And an interaction plot is nothing more than a plot of y-bars versus levels of one factor with y-bars for the other factor connected by line segments. So let me try to illustrate that with a picture for this glass phosphor example. All that we've got here is a plot of y-bar, that is current requirement. Y-bars from these various cells in this second table that we've written down here today, versus levels of one of the factors. And I happen to have chosen here to make a plot versus phosphor. Well, that's phosphor is factor B in this example. And so there are then 1, 2, 3, 4, 5, 6 means plotted. And there are 2 means for each level of phosphor, phosphor 1, phosphor 2, and phosphor 3. And those break into 2 groups. They break into a group for glass number 1 and a group for glass number 2. Glass is, of course, factor A. And what I've done is to connect with line segments the y-bars for glass number 1 and connect with line segments for the y-bars for glass number 2, and that gives this so-called interaction plot. In addition to putting the y-bars on this plot, I also put on this plot, just for our reference here, this also has the raw data values. So this is a little bit more than an interaction plot. It has plotted on it the individual data values, for example, 1, 2, 3 observations made with phosphor number 2 and glass number 2. That's a useful form of an interaction plot. It gives you a hint, for example, that the biggest thing going on in this experiment was the difference between the 2 glasses, that the glass number 1 and glass number 2 look like they have substantially different current requirements associated with them. There's also some hint that phosphor number 2 has larger current requirements than phosphor number 3. That's sort of the general visual impression that I get. There is the issue here of really how good are those plotted y-bars. So this is a useful plot as it is, but there's the question of how good are the plotted y-bar ij's. And we actually made an answer to that in Module 21. We could say to ourselves, we have confidence limits for mu's based on the y-bars of the form. If you go back and look at what we did in Module 20, they are, well, you take a y bar, now we're double subscripting for rows and columns, plus or minus t value, a pooled s, times the square root of what turns out to be 1 over the cell sample size. Here, that's y bar ij. As it turns out, if you look back in module 20, that's about y bar plus or minus 10.44 microamps. And a way to use that is to put error bars on an interaction plot. So let me insert another picture here. Very similar picture, but now I've erased, or I've taken out the raw data. The y bars are still plotted, but now what I've done is to make that difference about 10.44 microamps. That difference is about 10.44 microamps, and so on. That is, I've taken this idea of an interaction plot and I've enhanced it with error bars. So and where are those error bars coming from? Well, they're coming from these confidence limits for a mean based on this one-way normal model that we talked about in module 20. Now, looking at this plot, we get some sense that sure enough, there's a real gap between glass number 1 and glass number 2. There's sort of no way that I could slide those red dots around in those intervals and fail to have glass number 1 value current requirements above glass number 2. The question of whether phosphor number 2 is clearly above phosphors 1 and 3 is slightly less clear. You could sort of imagine perhaps sliding those red dots around until phosphor number 2 was no higher than phosphors 1 or 3 in those plots. So the point is that the size of the phosphor effects are not as big as the size of the glass effects. And the other thing to notice here is that this picture is more or less parallel, in the sense that I get about the same change in current requirement as I move from phosphor 1 to 2, no matter what the glass is, whether it's glass 1 or glass 2. I go up about roughly the same amount. If I look at going from phosphor 2 to phosphor 3, I get about the same size decrease in current requirement, whether it's glass 1 or glass 2. What I'm saying is this parallelism. So there's approximate parallelism on the plot. Basically allows me to think of the two factors, glass and phosphor, as acting in some sense separately on the current requirement. That is, in this picture, if you ask me what happens when I change from phosphor number 1 to phosphor number 2, I don't really care which glass you're talking about. You get about the same change in current requirement. That is, you move up from about here to there, or from about here to there, and that's about the same change. Or if I go from phosphor 2 to phosphor 3, I go down from about here to there. I go down from about here to there. Those two changes are roughly the same. And so I can possibly think about this situation involving a glass knob and a phosphor knob as one in which the glass knob does something, the phosphor knob does something, and what they do is in some sense separate from what the other one does.